So we've just established that NFAs are a thing that are interesting. We talked about their semantics. We talked about different ways of defining them with the oracle, with the one that produces the trace tree, which we call the forking model, the backtracking model. Now let's revisit what is interesting about them. The key thing that's interesting about them is that they allow us to easily define ways of combining um, DFAs together. So, as a simple example, let's look at another way of defining A union B. So A union B, we can define as an NFA in the following way. So imagine that we had a machine that this right here is the whole A machine. So it has some start state, it's got a bunch of transitions inside of it, doing all sorts of stuff. Then it's got some accepting states. Then we also have the machine B over here, and it's got this network of stuff, and then it's got its accepting states. Okay? Well, what we can do is we can define a larger machine that is the combination of these that works in the following way. Its start state is going to be a new distinguished state. It's going to have an epsilon transition to here and an epsilon transition to here. And then inside of each of these, there's going to be epsilon transitions out. And what they do is go to a final state. And let's think about how this would work as an NFA. How it would work is we would start here, and then we would non-deterministically decide which direction to go in. In terms of the backtracking model, that means that we would do both of them. We would do this one and this one, but we would do it gradually exploring them. And then eventually one of them would get to an accepting state, which would have an epsilon transitions out to the real accepting state. So this is a very simple way of defining the union. It's actually simpler than the one that merges them together and runs them in tandem. Now this picture right here, we can actually turn this picture into a real program as well. So let's look at how that program would work. So union is going to take one NFA. So it takes QA, sigma, Q0A, delta, which takes a QA, a maybe, sigma, and returns something in the power set of QA. And it has FA. It also takes QB, sigma, Q0B, delta, delta A, delta B. So QB cross maybe, sigma, arrow P, QB, FB. All right. And its output is going to be QC, Q0, C, delta C, and FC. All right, so let's look at the picture. So there is a distinguished new state right here and a distinguished new state right there, which is the accepting one. So that means that its states are going to be, let's call it start and end. Okay. And that start is going to be its start state, and the accepting states is just end. Okay. But now the states also contain everything that used to be in A and everything that used to be in B. Now there's a simple way that we can write this. So we can say we're going to union this with 0 cross QA and union it with 1 cross QB. So now what we've done is we've taken all of the states in A and paired them up with 0. Then we've taken all the ones in QB and paired them up with 1. Now we can look at the first element and see if it's from A or from B. Okay, now we have to define the delta function. So this is a little bit more complicated. So the first thing to look at is delta C of start. So if we look at its epsilon transition, well then it's easy because it goes to just two things. It goes to 0, Q0A, so that's the start state of A, and it goes to 1, Q0B, that's the start state of B. And on anything else, it's on C not equal to epsilon, it just is the empty set, because it doesn't have any other transitions. So that's delta C. So we've said what it does on start. Now let's look at delta C of end. So no matter what we're given here, we always go nowhere because there's no transitions on the end state. Okay. All right, what's next? So the next ones are quite easy. So delta C on 0 QA C is equal to, we're going to call delta A on QA and C. Then we're going to take that set that comes back and we're going to pair it with 0 because we go all to the same things. Then we're going to do one more thing, which we're going to union that. We're going to say if C is equal to epsilon and QA is inside of FA, that means it's one of the accepting states, then we'll return end. Otherwise, we'll return empty. So this basically says we take everything that the previous delta A did, combine it with 0, and then also do one more thing, which is that if C is the epsilon and QA is accepted, then we also go to the end. And there's a similar rule for the QB sets. It's literally the same. So 1 cross delta B, Q little b, C union with if C equals epsilon and QB is inside of FB, then we also have end, otherwise we have nothing. Okay, so now we've totally defined delta. So this right here is a very pedantic, tedious way of taking this picture right here and operationalizing it. I'm not going to do anything like that again, but we will draw pictures like this. So notice that this picture right here is a much simpler way of understanding how you can take two NFAs and combine them together with the union operation. Similarly, we can draw very simple pictures for showing the circ operation. And that's really, recall, why we were interested in these to begin with. Okay, so we want to do concatenation. Okay, so we want A circ B. So we have a little box for A. So we come in, it has all sorts of transitions, and it gets to the accepting stuff. Then we have B. We come in, it's got all sorts of transitions, and then the accepting states. Okay, well, what do we do? Well, what we do is we make it so that this larger box, we just have it so that the start state is that one, that there is an epsilon transition to the start state of there, and then these ones have an epsilon transition to an end state. Okay, so again, how can we write this down? So QC is going to be end, that's that distinguished end state right there. You know, do we even need that? Yeah, let's just not even need that. Let's just get rid of that. Let's just say that these are also the, they're the real end states. So that way we can get by with having fewer states. So we'll just have 0 cross QA union 1 cross QB. The start state, Q0C, is equal to 0 paired up with Q0A. The n states are 1 paired up with the n states of B. This whole pairing 0 with it in one of those is called tagging. Then what we do is we say that delta of 0 QA C is equal to 0 paired up with delta A of QAC unioned if QA is inside of FA and C is equal to epsilon, then we also go to 1 Q0B, otherwise nothing. And then we say that delta C of 1 QB C is equal to 1 cross delta B QB C. Okay, so that's really simple, right? So the idea here is that we always start at A, and then whenever A ends, we non-deterministically decide whether or not we're going to go over to B. And this is actually an important idea because we may keep going in A. You know what I mean? That's why it's a non-deterministic decision. There may be transitions from these start states back into A somewhere. That's what these are doing right here, because we're saying that we do whatever A was going to do, plus we do more behavior. We also might go to its epsilon transition. Okay, isn't that nice? Now, we've now come up with a way of writing down concatenation, unions. Earlier we talked about how we could do intersections, how we could do complement. There's a rich number of different things we can do. There's actually one more operation that is really convenient to have, and it's called the Kleene star operation. And let's come up with some examples first. So first of all, the way that we write it down is we write some set like B, and we put a star next to it. Okay, so that is the Kleene star operation. So when is something in it? So X is inside of B star if and only if X is equal to X0, X concatenated onto X1, concatenated onto X2, ... concatenated onto Xn, such that Xi is inside of B. So here's an example of that. Suppose that B was the set A, J, then something that would be inside of this would be A, J, J. That would be inside of there because it could be broken up into 1, 2, 3, 4, 5 different substrings where each one of them was inside of it. Whoops. Sorry about that. Where each one of it is inside of it. Alternatively, a way to define it is to say that if X is inside of the set containing epsilon unioned with B circ B star. That's an alternative way of defining it that notice is recursive because we have a B star on both sides. Okay? So there's actually a really simple way to encode this using NFAs, and it's the following. So imagine that we have our B machine, which I'll just put as a box right here. So that's our B machine. So what we do is we have a new state, which is accepting, and that's for when n is 0, and there's no substrings. And we have an epsilon transition into here, and then an epsilon transition out of here. Notice that here I'm abstracting a bit where I'm just drawing a box. What I mean by that is that if we have a circle that is pointing at a box, that means this is a state, and this is a machine, and we would say that this state goes to this machine's start state. And if we have a box that's pointing to a circle, then that means we have a machine pointing to a state, and we mean that this machine's accepting states go to that state. Okay, so this Kleene star operation is a way of introducing infinitely large things into our formulas for defining automata. For instance, you could ask the question, what is a formula? What's a formula for even length strings? So how can we come up with a formula for that? Well, it's actually quite nice. So what we do is we say we want 0, 1, circ 0, 1, and then we want to take that whole thing and we want to star it. So notice that this includes 0 because the star always includes 0, and then we have one thing and then something else. So that means that there's always going to be an even number. So this formula right here is even length strings. Now you may ask, okay, well, what is the formula for strings that are odd numbers? So strings that are odd numbers would be this. It would be 0, 1, star, circ 1. So that would be an example of odd numbers. So these formulas right here are a convenient way to describe different languages. And we're actually going to revisit this idea in just 2 classes with the concept of a regular expression, which I'm sure you've heard of in other contexts. But actually, there's kind of a fatal flaw with what we've done right now, which is, which is a little bit subtle if you are, if you're not particularly pedantic. And that subtle problem is that what we wanted was concatenation on DFAs. But we got concatenation on NFAs. And clearly NFAs and DFAs are different because, they're different things, right? The NFAs have the epsilon transitions. The NFAs can go this way or that way. I mean, they are actually different. And so given that they're actually different, who cares that we can do concatenation on NFAs? We wanted to do concatenation on DFAs. So what can we do? Well, recall the thing that I talked about in the very first lecture, that one of the things that we're really concerned about in this class is the idea that there can be multiple representations of the same concept. Okay, so what we would like to know is whether or not NFAs and DFAs are actually just different names for the same idea. In other words, are NFAs and DFAs equivalent? Are they equivalent? And what would it mean for them to be equivalent? What that would mean is that for all languages A, inside of, for all languages A, if A is a DFA, how do we even write this down? I mean, because the thing is that DFAs are machines and NFAs are machines, so how can we talk about there being the same thing? Well, there's 2 different ways that we can look at this. One thing is that we could define a larger category that they both are members of, or we could say something like, for all D inside of the DFAs, there exists an N inside of the NFAs where the language of D equals the language of N. Hey, in fact, we wrote that. That is the convert function. Because what the convert function does is it takes a DFA and it returns the NFA that does the same thing. Similarly, we could write a function that says for all n inside of NFA, there exists a D inside of DFA where the language of the NFA is equal to the language of the DFA. This would be a function that we'll call compile, because what it does is it takes an NFA, which is a complicated thing, and it compiles it to a DFA, which is a simple thing. That's going to be the subject of our next class. The other way to think about it is that NFAs and DFAs are both examples of a larger category. That larger category is something that we call the regular languages. Regular languages. And regular doesn't mean anything special, right? Basically, the people who came up with this field just thought that these were boring and simple, so they called them regular, okay? So regular languages are this larger category. Well, not larger, but it's this other abstract name. And we abbreviate it as reg. And we would say that everything inside of reg can be represented by a DFA, and everything inside of reg can be represented by an NFA. But reg are the actual things. Now go back to that very first lecture that we talked about. There's an idea of the set, and the set could be written down one way with curly braces, or it could be written down with a formula that's another way. So similarly, the regular languages are the actual, real, honest languages, the real thing. And one way to write them down might be with these formulas. One way to write them down might be as a DFA. One way to write them down might be as an NFA. They're all different ways of writing down the same idea. Okay, so if NFAs and DFAs are equivalent, then we should be able to convert DFAs to NFAs, and we should be able to convert NFAs to DFAs, and they're all examples of this larger category called the regular languages. This is true, and I'm going to demonstrate it next class, next lecture.